Hi, so welcome back. So where we stopped last time was that we were trying to do, solve the bundle equations for a set of bodies other than a flat plate, right? So we were using transformed coordinates, which is localized coordinates basically. So which is zeta and eta, right? So this is how we said zeta and eta, and using that, and we came up with a trial solution, which is given here in 3, right? And using that, we came up with a solution. We basically wrote out the expressions for u and v in terms of the zeta and eta. And then we input this into the Bundle-Larry equations, and what we get is this 3, right? So this was the equation that we get, where alpha 1, alpha 2, and alpha 3 look like this. Okay. Now, clearly, what we said before stopping last time is that this equation, right? So this equation here right? So this equation here, right, is a PDE, right, is a partial differential equation, as you can see, for f, zeta and eta, right? Now, the question I had posed to you last time is that what happens if alpha 1, alpha 2, and alpha 3 are constants, right? So if you have some basic idea about differential equations, you will see that if alpha 1, alpha 2, and alpha 3 are constants, right, then equation 3 basically reduces, right, to an ODE, an ordinary differential equation for the function f of eta, right, that is del f del zeta is 0, right. So which means that if alpha 1, alpha 2, alpha 3 are constants, equation 3, let's put it this way, equation 3, so let's say equation 3 is a PDE for this thing, but if alpha 1, alpha 2, alpha 3 are constants, equation 3 reduces to an ODE, ordinary differential equation, for f of eta, right? That is, that solutions to f of zeta eta can be found that are independent of zeta, right? So essentially what that means is that solutions to f of zeta eta can be found, right, that are independent of zeta, so which are independent of zeta, right? That is, like we just now wrote, f of eta. So now it's basically a function, f is basically a function of just eta, one variable, okay? So therefore, so we rewrite equation 3 to be the ODE, right? So transform to ODE, and that looks like f of, okay, plus this is a constant, f of f double dash, plus alpha 2 minus alpha 3, okay? And since now this is a function of only eta, so you can see on the right hand side, okay, del f del zeta will be 0, right? And del f dash del zeta will also be 0, right? Because it's a function of only eta. So what we get on the right hand side, so the right hand side completely goes, right? So this is therefore an ODE. Let me call this as 4. So this is an ODE, right? So is an ODE for f of eta. Is that right? Okay. So therefore, here in that case, what are the unknowns? When we have alpha 1, alpha 2 and alpha 3 are constants, okay? So as per this equation, what are the unknowns? Okay? What are the unknowns in this case? Okay? So which is right. So, well, in particular, of course, solutions exist for u infinity zeta for the outer flow, for which similar solutions are available. Okay, so we will, sort of now elaborate on this a little bit as to, again, what are we looking at? So these are things. So similar solutions, again, we will classify this. Okay, we will classify this. So similar solutions are classified as, say, A. Okay. A, boundaryless with outer flow. Okay. With outer flow, that is u infinity zeta is not 0 and boundary layers without outer flow, that is u infinity zeta is equal to 0. So, right. So basically, we're going to look at all sorts of combinations. So usually we do a lot of these, things, because when we get a numerical equation, our main focus is how we can solve it. So we try a lot of permutations and combinations, but of course, when we finally get a solution, we try to really understand it and try to make sure that it does mean something physically and it's not just a numerical exercise, right? And if it doesn't, then we're not sure to stick with that kind of we don't call it a solution exactly. Okay, so that's what we'll do. So boundary layers with outer flow and without outer flow. So which means that u infinity, zeta may or may not be 0. Okay, so let us go and look at this. So we will look at several cases. So one of the cases, so say case 1. Okay. Okay, so u infinity zeta is not 0, right? It is not 0. So then what we will do is we will set, okay? So we will set un zeta is equal to u infinity zeta. Okay, so if we do that, if you do that, right? If you see un zeta is equal to u infinity zeta. Okay, so if I do that, okay, so what happens? U infinity un basically is equal to u infinity zeta. Right? So basically alpha 2 becomes equal to alpha 3 if you see from here. Okay? So if I do that, so then what happens to, okay, so let's do that. So in that case, the moment we do that, so this implies, okay, this implies alpha 2 is equal to alpha 3. Okay? Now, so having said that, that is there. Now we will look for alpha 1 being positive, negative or 0. Okay, what we will try to look at is whether alpha 1 is positive, negative or 0. Okay, now so let's say this is case A dot 1, where this is alpha 1 is equal to 1. Okay, alpha 1 is equal to 1. Okay, so basically it is positive and we are setting it equal to 1 without any loss of generality. Okay, so well, you can explain this to yourself, but let me sort of elaborate on that a little bit. So now alpha 1, so alpha 1 is essentially this. So delta star by V infinity ddz of un. So un is nothing but u alpha zeta, right, delta. Now this delta bar length scale, right, is only a certain percentage of where it achieves the V infinity, right, that where it is able to recover the complete free stream velocity, right. So therefore this delta bar, the maximum, right, it's only a percentage, so the maximum can only be 1, isn't it? The maximum can only be 1. Okay, so now so we'll just say alpha 1 is equal to 1, right, alpha 1 is equal to 1. Okay, so then we will let alpha 2 equal to alpha 3, and we're going to call this as beta. Okay, then what happens to equation 4? If you see that, what happens to equation 4? Okay, so what happens there is, okay, so we get, so this is from 4, so we got that, okay, plus alpha 1, okay, we're going to write that alpha 1 f of f double dash, okay, plus okay, let's just see what was my equation. Okay, I think I sort of made a small mistake here. Okay, f dash of square, sorry about that. Okay, I missed that term for some reason. Okay, sorry about that. So this is our equation. Okay, fine. So once we do that, so then that's our equation, and if I come back here, so then of course alpha 2 is equal to alpha 3, so 1 minus f dash of square, beta is equal to 0. So this is, so we get another equation which is like this, right? So that you can see here that this is again for a specific, specific case. So we have a different equation to solve, and anyway alpha 1 we are setting it as 1, okay. So this one I'm going to call as 5, okay, and this equation, okay, is called the Falkner-Skan equation, right? It's called the equation, and it's kind of first proposed around 1931, okay. And the solution and dependence of beta is also, well, when you kind of come up with equations like this, like I said, I mean, you get a solution and then you really have to study the solution hard to see, what implications does it have physically and whether it even means anything, okay. So the solution and dependence of beta was also examined by Hartree, okay, and this is basically accompanied by the following boundary conditions. So the boundary conditions, okay, eta is 0, f is 0, f dash is 0, eta is large, f dash is equal to 1. Right? So what we get here in this particular case is the Falkner-Skan equation, okay, and let us see what we will write here. So for this case now, so alpha 1 is equal to 1, okay. So if alpha, so what do we get? So since we said alpha 1 is equal to 1, so let us write this here, okay. Then alpha 1, okay, is equal to delta bar by V infinity, right? Yes. Okay. d zeta of un delta bar, right, then this is equal to 1. Okay, this is 1, and let's say this is six. Okay, and again alpha 2 is equal to delta bar square by V infinity u infinity un du infinity d zeta, right, is equal to alpha 3, which is equal to delta bar square V infinity dun d zeta, which is equal to beta, right, which means that delta bar square by V infinity, yeah, well, du infinite, d is equal to beta, correct, dun d zeta. Okay, so now as you can see here, so we can get an expression for beta, right? So here it's equal to that. You can see these are equal because u infinity, un we will set that un equal to, so we set that we will set un equal to u infinity, right? So if I do that, then this term becomes 1, right? So this term basically is 1, right? So that makes alpha 2 equal to alpha 3, right? So that, right? So that delta bar square by V infinity d u infinity d zeta, right? Yeah, well, you know, so the un is again equal to u infinity, so that's fine. Okay, so but anyway, I will write that down, delta bar square, again, V infinity, del un d zeta is equal to b. Okay, is equal to b, and I'm going to call that seven. Okay. Okay, so now, of course, so we've got an equation. This is an important equation. So Falkner-Skan equation. So we get this, right? So this is a particular case, right, where we are considering a boundary layer with outer flow. Okay, and we set the un zeta to this. Then we set alpha 1 equal to 1. Okay, it's just positive value, right? And so we get something like, you know, this expression. So now So, Blasius, now the question is that Blasius observed that if the outer flow, okay, observed power law, right, then we could have basically similar solutions, right. So, right, so what this is actually from numerical condition, numerical considerations of the numerical solution, that Blasius, he observed that if the outer flow, right, so if the outer flow, okay, followed a power law, right, we could get similar solutions. Okay, so let us see whether it is we get something interesting or not. If that makes any sense to us, let me see what he means by that. Okay, now let us say, which means that say something like this. Okay, I'm going to write it here itself. So what he means is that if u infinity by v infinity is equal to, this is some constant zeta to the power m, right? It's trying to follow a power law. Okay, so the outer flow, right, which is un or u infinity by v infinity, is b zeta to the power m, and b is a constant. Okay, b is a constant. Okay, and this m, the power, okay, the power is beta by 2 minus beta. Okay, so if I do that, so beta is something that we get from here, right? So if we do that now, okay, so now if you see this, if you see this equation 6, right? So now you see, now from 6, okay, so we're going to expand this integral basically. Okay, so what we're going to do is delta bar by v infinity. Okay, this is going to be un, okay, d delta bar d zeta, okay, plus delta bar dun d zeta is equal to 1. Okay. Now, if you see equation 7, okay, delta bar square by v infinity into dun dz is equal to beta, right? Which means, right, if I were to open the, remove the brackets, right, remove the brackets here, so what I would get, so if I remove the brackets, okay, this is this by v infinity. But then this term is actually beta, if you see from 7, right? So if that is true, then, right, what can we write? So then what we can write, therefore, okay, therefore delta bar un by v infinity d delta bar d zeta plus beta is equal to 1, right? Or we can just say that delta bar, yeah, okay, fine. Okay, so we've got this. Now this un, right, un by v infinity. So now again, so we know that un is equal to u infinity, right? So if I were to, so essentially what I have here is u infinity by v infinity, which now is equal to b zeta to the power m, right? So if I do that, so therefore then I can write here, right, so this bit, right, or, so what I can write is or delta bar, okay. So yeah, so delta bar un, okay. So un by v infinity, this is nothing but beta zeta to the power m, okay, d delta bar d zeta is equal to 1 minus beta, right. So if I write this, and again m is equal to beta by 2 minus beta, right, we've got that there, okay. So if I do this, okay, so now we've kind of got to do this you know, solution which is simple now. So let me write it down and let me see if I can do this, or I will post it for you, okay. So basically what we get here, so I'm going to sort of rush through this a little bit, okay, not spend too much time. So delta bar d delta bar, okay, which is, okay, please note that, so this is d delta bar, okay, is equal to 1 minus beta, okay, by zeta to the power minus m d zeta, right. So this is essentially you know, my integral equation, which is coming like this. Now if I then integrate, okay, or b integral delta bar d delta bar is equal to 1 minus beta, okay, integral z to the power minus m d zeta, okay. So or b delta bar square by 2 is equal to 1 minus beta zeta to the power minus m minus 1 by minus m plus 1. Okay, so or delta bar, okay. So well, I mean, I can just skip a couple of steps, okay, maybe not. Delta, you know, square is basically equal to 2 by b, okay, into, okay, now you see m, okay, if you see this, m is equal to beta by 2 minus beta, okay, or 1 minus beta is equal to 1 minus m by 1 plus m, okay, that I get just from there. So you should be able to get that. So then 1 minus beta is nothing but 1 minus m by 1 plus m, right, into zeta to the power 1 minus m, okay. Okay, I think I got that wrong. Did I get that wrong? Yeah, okay, yeah, I mean this should have been plus, right? This should have been plus, sorry. So then I get 1 minus m by 1 minus m, right? So if I do that, or delta bar square is 2 by b, okay, into 1 plus m, okay, into zeta to the power 1 minus m, right? Or finally, or I take the square root, delta is equal to 2 by b 1 plus m zeta. So, okay, zeta to the power 1 minus m by 2. Okay, so that is essentially, so therefore this is my equation, that is 7, so this is 8. Okay, this is a solution, right? The above solution is, so if I carry out the solution, okay, so the solution, right, is that beta is not equal to 2. That's something, it's important, right? Beta is not equal to 2. Okay, you can check that. So I would like you to just sort of think that if this is the solution, what does this even mean? What happens? So what happens? I'd like you to think. I can discuss this in the next module, but I would ask you this. So let me know what happens if beta is equal to thing. So what we will do is in the next module is, now that we've got an expression for this delta star, so basically what we will get is a function of eta, like we did previous case for the flat plate, right? So we will get an expression for eta, right, for y and x, and then that should give us a that should basically give us a solution, right? So we will see where we end up doing that, right? So we shall continue with this in the next couple of modules, and we look into that. Okay, so let me kind of summarize. So what essentially we did here is we're looking at solutions to other than two bodies other than flat plate, and what we've been able to do is right now we're kind of classifying problems. Okay, we do get an equation like 4 here, so we do get an equation like 4, and it is an ODE. Okay, now what we do here is that it's a complicated equation, so we're kind of classifying it. So there are two cases. One is when the boundary layer is with outer flow, and the other is without outer flow. Okay, so now when I do that, so the first case is so boundary layer is without outer flow, and we set un equal to u infinity here, and then we set alpha 1 is equal to 1. So basically we're looking at solutions for alpha 1 to be positive, alpha 1 to be positive, negative, or 0, right? So the case we considered here is basically alpha 1 is positive, and we've set that equal to 1 without loss of any generality. Okay, and then we continue so far. So this is the equation. So what we land up with when we do that, so we get alpha 2 is equal to alpha 3, we land up with the Falkner Skan equation, and we have finally come up with, and we saw that, and Blasius saw that if the outer flow obeys a power law, we could get similar solutions. So what we've landed ourselves up with an expression for the delta bar. So now we're going to try and get a solution for this, using getting into eta. So we shall do that in the next couple of modules, and I'll stop for now. Thank you.